On this video, I will narrate the results of a finite difference calculation of the Schrodinger equations mode of a cosine slash parabola potential. The potential is shown here by the black curve, and it has a lower potential well minimum and has an upper potential well minimum. I also show the velocity versus position of a particle that we've put in this potential well. In this case, the energy of the particle is here at the red line, that must be 1.42 joules. And for this calculation, I'll have the Schrodinger, the Planck constant, rather, h bar 1 kilogram meter squared per second. And so then the mass, I'll also have 1 kilogram. So it's a very simple calculation that way. Okay, in addition to the velocity versus position, I also show the green line, which is the green curve, rather, which is the 1 over the absolute value of the velocity. That should correspond to the magnitude of the Schrodinger wave function squared. So I also show the motion of the particles here. So you see that the black, well, there are all three particles move in unison and actually have, they're all really the same three particles. And the black one moves along the potential curve, the green one along the 1 over velocity curve, and the orange one parallel to along the velocity curve, velocity versus position. So, next thing I'd like to show is what happens when you calculate a mode for this potential. So we'll calculate some modes and show what you get. So for simplicity, we'll look at the smallest, lowest energy first. Now here's the lowest energy. And you can see it's very, very low, and of course the particle is not capable of moving very far back and forth in the lower potential well. And the next mode up is actually, well, the first mode, of course, is just a Gaussian. It happens to be positive on the right-hand side, negative on the right-hand side, and negative on the left-hand side. Second mode is just really the derivative of a Gaussian. And the next mode in that is just a Hermite polynomial multiplied by a Gaussian. Hermite polynomial, the first excited state is just x, 2x. The next mode pair, really, see, this is the other part of this thing. Next mode pair is shown here, and here we have we have Hermite 2 centered on the left-hand side and also centered on the right-hand side. And so these are just the standard harmonic oscillator wave functions, one centered on the left potential well and the other centered on the right potential well. So the next one that I'd like to show is okay, next I have, for this particular calculation, the energy exceeds the bottom of the upper potential well, and that means that that one will be populated. And the first one that's populated is on the right side, and the second that's populated is on the left side. Next we'll show the next mode, and we're back to center again. Now we have Hermite 4 populated on both the right and the left side of the lower potential well. Same thing here. And okay, so now we have Hermite 5 times the Gaussian, left and right. Hermite 5 again, and now we have Hermite 1 on the upper potential well on each side. And here is the next one. It's the opposite handedness for the next H1. Next we have a higher mode in the center, and at this point I'll introduce the concept of velocity. You see the n, its equivalence to the k vector of the spatial frequency of the mode. Here we have a dotted line. It's which is really the value of h bar k over m, which is in quantum mechanics the velocity. And we also have the solid line, which is the corresponding thing in classical physics. And they go over here. Now there's no waves shown on the left-hand side here or on the right-hand side, but we really do have a small frequency there. So the waves are just really low amplitude. So notice the good correspondence numerically between the two waves. So it's 1.35 for the classical speed, and for the quantum speed is 1.46 meters per second. So we have the same thing here, because all the modes, by the way, here's a fourfold degeneracy, or nearly degeneracy. Here we have Hermite 3 on both the left and the right hand side, and it's a repeat again, twofold degeneracy. Now here we're going back to a non-degenerate mode, and we have a higher Hermite polynomial. However, you can't expect these to remain nice and simple parabola solutions anymore, because the energy is quite high compared to the value of compared to the height of the mode. I'm sorry, compared to the height of the potential barrier here. So next thing we show is now the energy has exceeded. Notice the energy has now exceeded the center peak. That means that you can have significant population over the center of the potential, because it's high enough. And there we have the significant population I was talking about. So you have the square of this function is actually the population of that value. Notice the good agreement between the velocity, quantum mechanical velocity, and also the classical velocity. Quantum mechanic dash, classic solid line. Now we have higher modes here, and we'll continue on up till we get to the point where we have significant. Okay, here we've exceeded the energy needed to get for the classic particle to get over the peak in the center, the second peak, and therefore you have a continuous distribution of all the way. Well, you have the classical particle can move all the way from left-hand side to the right-hand side of the potential. Except, of course, it turns around. The classical mode turns around here where the red line runs into the green line. I'm sorry, into the potential line. Of course, now it's an important point here. Even though the classical turns around, that does not mean that you don't have any population for the quantum mechanics. And you can see that there's a certain amount of tunneling beyond this position. This be about right here. It tunnels from here on over, and from approximately here on over. So there's effectively have an evanescent wave going beyond the classical boundary. So continuing on upward, we have pretty good agreement between the quantum velocity and the classical velocity. Quantum, again, is broken line. Classical velocity is solid line. The next, continuing on up to a higher mode, yet we have not quite as good agreement. There's some overshoot here on the quantum velocity, but not too bad. And in fact, these are numerically, there's no scaling here to speak of. So we have good results. Another thing I want to point out is that if you average the quantity h bar k squared over twice the mass over the entire range of the particle, well, entire range where you can actually calculate the frequency, you see that it agrees very well with the actual mode frequency, 1.34 divided by, or compared to 1.59 joules. Continuing on up, we have, again, pretty good agreement with between the classic quantum velocity and the classical velocity, but less so. And that might be attributed to the fact that it's very hard to get really good calculations of the modes at higher mode numbers using finite difference calculation, which is what is being done here. And here we have it again. The agreement gets worse. Notice that back down here, the agreement is really quite good between quantum velocity and classical velocity. Here too, and worse here, and we'll go all the way up. Much worse here. Basically, what you're running into is what's called the Nyquist criterion, which means that you have to have more than two points per cycle in order to do a decent calculation of the Fourier transform of the wave, which is really what you're doing when you're calculating the Schrodinger equation wave function. So we're much better off down here than we are up here. Okay, before I leave, I want to point out that the time that the classic velocity spends at the top of its trajectory here, which is in 1 over velocity space, which is up here, is much longer than it would be in another, well, much longer than the case for quantum mechanics. That just happens to be true. So really, the correspondent difference principle, which we're talking about, does not apply very well at all to the time-independent Schrodinger equation. It does apply much better to the time-dependent Schrodinger equation. So there you have it. That is the result that you get from when you do a finite difference calculation of the modes for this cosine / parabola potential.